Welcome to the Deep Dive, where we unpack the latest in AI research. Today we're looking at a really interesting paper on process reward models, or PRMs.
Ah, yes, PRMs. They're pretty vital, aren't they, for scaling up how large language models reason?
Exactly. Helping them, check their step-by-step work and figure out the best way forward.
Right. And the standard way, historically, has been these discriminative PRMs.
Yeah, the ones trained to just say correct or incorrect for each step.
But that takes a ton of labeled data, step-by-step annotations. Very expensive.
Then came this idea of LLM-as-a-Judge, using the LLM itself for verification.
Yeah, generating text to verify, no specific training needed, which is great for data efficiency, and you can kind of see its reasoning.
But not always the best on really complex stuff, right?
Exactly. It can struggle when the reasoning gets deep. So this paper digs into a really key question. How do we get the best of both worlds?
How do we mix that data efficiency and the interpretability of LLM as a judge?
With the raw power, the performance of those discriminative PRMs.
Okay, so for everyone needing the quick version, the headline, this paper introduces ThinkPRM. It's a generative PRM.
Right. It verifies by generating its own chain of thought, its own reasoning about the solution steps.
And here's the kicker. It's fine-tuned using way less data, like just 8,000 process labels. Compare that to the massive data sets for discriminative models.
Huge difference. And the results, well, I think PRM actually outperforms LLM-as-a-Judge and those data-hungry discriminative ones on some tough benchmarks.
And it scales verification compute really well, too. Okay, let's unpack that. What's the core idea behind ThinkPRM?
Well, the main insight is that, while using an off-the-shelf LLM as a judge has problems.
Yeah, the ones we just mentioned.
Their ability to verify can actually be boosted quite a bit if you give them more compute time during inference, specifically by getting them to generate a detailed chain of thought about the verification itself.
Okay, so instead of just the thumbs up or thumbs down, you're asking the LLM verifier to, show its work, kind of mirror the original reasoning process.
Precisely. Show me why you think this step is right or wrong. And to do this, the researchers cleverly repurposed existing open-weight, large reasoning models.
Models already good at that chain of thought stuff.
Exactly. Models built for reasoning. And they turned them into these generative PRMs with just some lightweight fine-tuning.
Lightweight?
Yeah.
You mentioned the 8,000 labels. That sounds incredibly light.
It really is, compared to, the hundreds of thousands or even millions of step-level labels some discriminative PRMs need. It's a game changer for practicality.
Wow. That's a massive difference in data needs. So how do they actually train these ThinkPRMs? Walk us through that.
Sure. So they fine-tuned 4 different reasoning models. There were 3 sizes of R1 distillquin, 1.5 billion, 7 billion, and 14 billion parameters.
Okay, different scales.
And also QWQ 32B preview. And remember, more parameters generally means more capacity for complex stuff. But what's really striking, especially for anyone who actually trains these things, how efficient the training was. The biggest one, the 14 billion parameter ThinkPRM, they trained it in just 4 hours.
4 hours. On what kind of hardware?
A single A100 80GB GPU.
That's seriously fast for a 14B model fine-tune.
Yeah.
Incredible. And what data did they use for this super efficient tuning?
Mostly synthetic data.
Okay, generated data.
Yeah, generating potential reasoning steps and the corresponding verification chains. But the crucial bit was ensuring quality. They used those 8,000 real process labels as a guide, sort of, to generate and then filter the synthetic data really carefully.
Got it. So quality control on the synthetic stuff, guided by a small amount of real data. Now, ThinkPRM generates this verification chain of thought. What are the big advantages the paper highlights?
Well, there are a few key benefits, especially for us researchers and engineers. First, interpretability. Big one.
Right, you see the why.
Exactly. Because the verifier generates its reasoning for each step, you get way more insight into why it thinks something is correct or incorrect. It's not just a black box score, it's a justification.
That's huge for debugging and understanding what the model's actually doing. Way better than just a binary pass-fail. What else?
Scalability. Because ThinkPRM is generative, you can scale the compute you throw at both the original model generating the solution and the ThinkPRM doing the verifying.
So at test time, you can decide to spend more compute if the problem's harder or needs higher confidence.
Precisely. You can strategically invest more compute power for more reliability.
And the third big one you mentioned earlier, data efficiency.
Yep. By building on models that already know how to reason and using clever synthetic data techniques, ThinkPRM slashes the need for all that expensive labeled data you'd need for a traditional discriminative PRM.
Okay, so the paper digs into some specific research questions to back this up. RQ1 looked at the limitations of just using standard LLMs as judges, right? The baseline approach. What did they find there?
Yeah, they ran into several pretty significant issues. One was high sensitivity to how you word the instructions.
Oh, prompt sensitivity.
Exactly. Small changes in the prompt could make the accuracy swing wildly. Not very reliable for real use cases.
Yeah, that's a classic problem. Makes it hard to trust. What else?
They also saw models generating invalid judgments quite often. Basically, the verification output didn't give a clear, correct, or incorrect label.
Why would that happen?
A few reasons. Sometimes the model would just start trying to solve the original problem itself, instead of verifying the given solution.
Right. It gets sidetracked.
And they also saw this thing they called overthinking. The model generates these incredibly long, rambling verification chains.
Like it's stuck in a loop.
Yeah, sometimes getting stuck in loops or just repeating itself, never really landing on a clear judgment.
So the verifier kind of gets lost. The paper mentions process bench data showing this.
It does. On some tough subsets, like Olympiad Bench and OmniMath, the LLM-as-a-Judge approach just didn't perform well. The F1 scores, which measure verification quality, were pretty low.
Indicating it wasn't reliably verifying complex reasoning?
Right. And they even found a pattern. The inaccurate chains, the ones doing all that overthinking, tended to be much, much longer.
Okay, and there's a figure 4 in the paper about this.
Yeah.
The length distribution.
Yes, figure 4, the left side, it really shows it clearly. You see a blob of accurate verifications at a reasonable length, but then this long tail of inaccurate ones stretching out to thousands of tokens.
Visually confirming that overthinking problem.
Definitely. And if you want to see actual examples of the looping and rambling, Appendix B, figures 15 and 16, has some good ones.
Okay, so LLM-as-a-Judge on its own has issues. That leads to RQ2. Can fine-tuning on synthetic verification data fix this? What do they find?
The results were really positive here. Even that lightweight fine-tuning, using carefully made synthetic data, made a huge difference. Performance went way up.
And they use that filtered synthetic data to avoid needing tons of real data, right? How did that filtering actually work again?
They called it rejection sampling fine-tuning. So they'd get a powerful model like QWQ32B to generate lots of possible verification chains.
Okay.
Then they'd filter these generated chains. Did the step-by-step judgments match the gold labels from a known data set like PRM 800K? Did it follow the right format, give clear labels? And crucially, was it too long?
Filtering out the overthinkers too.
Exactly. Keep it concise and accurate. Figure 5 in the paper lays out this whole data pipeline visually.
So using a reference data set to check the synthetic work, and you said the fine-tuning itself was fast.
Yeah, remarkably fast. Like fine-tuning that big QWQ32B model took only 4.5 hours on one A100 GPU. Very practical.
Okay, and the impact. What happened to the scores after this tuning?
Big improvements. F1 scores jumped up significantly across all the models they tuned. That's in Table 2 and Figure 7. The smaller 1.5B model saw the biggest relative boost, actually. And importantly, the number of those invalid judgments, that dropped way down. Figure 6 shows that.
Fixing a key problem of the baseline.
Right. And the overthinking. Figure 4, the right side this time, shows ThinkPRM's generations are much more controlled in length, staying reasonable while being much more accurate. Less looping, less rambling.
Okay, that sounds like strong evidence for the fine-tuning approach. So RQ3 compares ThinkPRM to baselines when you start scaling things at test time. How did they set up those comparisons?
They mainly used the 1.5B and 14B ThinkPRM models, and they compared them against several things.
Like what?
DisPRM, that's a standard discriminative PRM trained on the full PRM 800K dataset, using the same base model architecture as ThinkPRM. Also, the baseline LLM-as-a-Judge using that same base model, and just simple majority voting over multiple generated answers.
Okay, a few different comparison points. How do they actually use the verifiers?
For best of n, where you generate multiple solutions and pick the best, they used a weighted majority vote based on the verifier's score. Higher score means more weight. For guided beam search, where the verifier helps steer the generation process, they picked the final answer that showed up most often in the search beams.
Got it. And what kind of tasks did they test this on?
A mix. Some math problems like Math 500 and AIM 2024 questions. Those were kind of in domain. Then for out-of-domain tests, they use GPQA, diamond physics questions, and live code bench for coding.
A good range. And they use different generator models, too.
Yeah, they mixed it up with different Quen and Llama models to make sure the results weren't just tied to one specific generator.
Okay, makes sense. Let's get to the results then. Best of N selection. How did ThinkPRM do?
Figure 8 shows this pretty clearly. ThinkPRM 14b scaled better with accuracy as they generated more answers. Increased N on both math and AIM tasks. Better than LLM-as-a-Judge, better than the DisPRM, and better than just simple voting.
So it was better at picking the right answer out of a crowd of possibilities.
Seems so. It's just ThinkPRM is more discerning when given more options.
What about guided beam search, using the verifier during generation?
Figures 1 and 9 show ThinkPRM 1.5b beating the discriminative DisPRM by about 5% accuracy on Math 500 in that setting.
5%. That's quite significant.
It is. It suggests ThinkPRM is better at actually guiding the generation towards correct solutions.
Especially impressive given ThinkPRM used so much less training data. How did it compare to other PRMs out there, ones people might already be using?
Also quite well. Figure 9 shows ThinkPRM 1.5b actually outperforms some other public PRMs like RLHF Flow DeepSeek PRM and Math Shepherd PRM, even though those were trained on much more data.
Really? Wow, that really speaks to the efficiency of the ThinkPRM method.
Yeah, it's quite compelling.
Okay, but what about out of domain? That's always the acid test for generalization.
ThinkPRM held up well there too. On the GPQRA physics questions, it scaled better than DisPRM as they sampled more solutions, ending up about 8% higher accuracy at N32.
8% better on physics, having been trained mainly on math-like data.
Yep. And on Live Code Bench, the coding task, ThinkPRM beat DisPRM by 4.5%. Figure 11 shows these results. And they contrast this with another discriminative PRM that was trained specifically on math data. It really struggled on these out-of-domain tasks. So ThinkPRM seems to generalize better.
Interesting. The paper also looked at scaling the verifiers compute directly, right? Not just generating more solutions.
Yes, they looked at parallel and sequential scaling of the verifier.
Parallel scaling meaning?
Generating multiple verification chains independently for the same solution step, then combining the judgments somehow, like averaging or voting.
Did that help?
It did. Figure 9 shows ThinkPRM 1.5b getting a boost of over 5% on Math 500. Just by running 4 parallel verifications, they denote that as at 4. And figure 20 in the appendix shows similar benefits for the 14b model too.
Okay, so more verification compute helps. What about sequential scaling?
That's where they had ThinkPRM basically recheck its own work, prompting it again like, okay, let's verify that step again.
Oh, does that work?
Apparently, yes. Figures 2 and 21 show ThinkPRM scaling better this way than the baseline LLM-as-a-Judge. And it even beat the big DisPRM 14b by 15 F1 points on a process bench subset using the sequential checking.
15 points. That's a massive improvement.
It is. And interestingly, the overall gains from parallel versus sequential scaling seem pretty comparable in their tests.
Okay, back to data efficiency. You said ThinkPRM needed way less data. Did they analyze that specifically?
They did. Figure 1, the left side again, is really striking here. It shows ThinkPRM 14b trained on just 500 or 1,000 examples. That's only like 4,000 to 8,000 actual step labels.
Tiny amount.
Outperforming the DisPRM 14b that was trained on the entire huge PRM 800K dataset. Orders of magnitude more data.
That's incredible efficiency.
And they also found that training ThinkPRM on even more synthetic data, like 65,000 examples, pushed performance up further, so there might still be room to grow there.
And you mentioned that the way they filtered the synthetic data was important. Process-based versus outcome-based.
Yes, huge difference. Process-based filtering means they checked if the step-by-step reasoning in the synthetic verification matched the gold standard steps. Outcome-based just checks if the final answer was right. Figure 10 shows process-based filtering was way better, leading to much stronger PRMs, even when using less filtered data overall. So focusing on the reasoning process itself for this synthetic data quality is key.
Makes sense. You want the verifier to learn the right process, not just guess the outcome. Did they look at how ThinkPRM handled harder versus easier problems?
Yep. Figure 12 breaks down performance by difficulty on Math 500 and GPQA physics. And ThinkPRM showed a noticeably bigger advantage over DisPRM on the harder problems in both datasets.
So its detailed verification approach pays off more when things get really complex.
Seems that way. The chain of thought verification seems particularly helpful for catching those subtle errors in difficult reasoning.
Right. Now, no silver bullets. The paper must mention some limitations of ThinkPRM too.
Of course. They do point out a few things to keep in mind. One is potential overconfidence in the scores.
Like the model saying it's very sure even when it's wrong.
Yeah, sometimes the scores, which come from token probabilities, might not perfectly map to actual certainty. It's a common LLM thing.
Okay. What else?
There's a potential issue called step label interference. Basically, if the verifier makes a mistake judging an early step in the reasoning chain,
It might mess up its judgment of later steps.
potentially, yeah, the earlier error could bias later evaluations. And the obvious one. Generating these long verification chains takes more compute time and resources than just getting a simple score from a discriminative model.
Right, computational overhead.
Exactly. But as the paper argues, the performance benefits, especially on tough tasks and with the data efficiency, often make that extra compute worthwhile.
Okay, so let's wrap this up. What's the big takeaway here? The main contribution of ThinkPRM.
I think the core contribution is really showing this generative approach to process verification works and works really well. ThinkPRM is data efficient, it's scalable, it's interpretable because of the chain of thought.
And it outperforms existing methods in many cases, even ones trained on way more data.
Exactly. It provides a really strong alternative to discriminative PRMs and tackles the weaknesses of the simpler LLM-as-a-Judge approach.
It feels like a significant step forward for building more reliable AI reasoning systems, especially for us working in this field.
I agree. The results on tough benchmarks, the scaling, the out-of-domain performance, it's all very promising. And doing it with less data is huge.
Yeah, it suggests generative PRMs, like ThinkPRM, could be really key for pushing the boundaries in complex areas, math, science, maybe even code generation.
Definitely. Getting models to reason about the correctness of reasoning itself, not just the problem that seems like a powerful direction.
So here's something for you, the listener, to chew on. We've talked about these trade-offs: interpretability, data needs, compute scaling. How might these generative PRMs, like ThinkPRM, fundamentally change how we develop and deploy AI reasoning systems down the road? What does this mean for the kind of research we should be doing or the systems we're trying to build?
It's a great question to ponder. And for anyone who wants to get hands-on, the paper mentions the code, the data, and the models themselves will be released. Check the links in the paper for that.
Fantastic. Well, thanks for joining us for this deep dive into ThinkPRM.